Okay, we're gonna work on the Aquarius symbol. So, we're thinking just a zigzaggy kind of pattern for that. Let me see if I can find this in my history. Now we're gonna have to find it again. Okay, so there's many ways you could like draw this symbol, but I'm thinking some type of zigzaggy, rounded zigzaggy pattern would be the easiest. So not this. I mean, that'd be kind of nice. It looks more like water. But I'm trying to think in terms of what's going to fit with what I'm already doing. I don't know. I kind of like a zigzag pattern, but just rounded. So something like this one, something like this is what I'm thinking. So like this, I'm thinking this, but then we chop off the tips here and make them kind of square. Oh, there goes my bit rate. So let's open this up in a new window so we can use this for reference. But yeah, I think this is what I want to go with. I also have, I'm not just working off of one thing. Also, I'm using this as reference. Right, so you see how this looks like a whole bunch of M's. Right, so that's why it's important to look at, to have more than one piece of source material. Because there's many different stylizations, and you have to figure out, well, what's the core, what's the essence of the symbol, right? What's going to be most easy for people to recognize, right? So, let's get to it. So the first thing you want to do is you want to go into the cutting files, and let's just open up one of these things. Let's open up with Notepad++, and that's not actually where I wanted to open it. Let's put this over here. Okay. So, we're going to copy this, and we're going to make a new file, right? So we're going to go File, New. And for Aquarius, right? Aquarius, it's going to be AQU, Aquarius, right? And this is just like a stub function for when we're finished. The idea here is that we want to have the file. We want a 1:1:1 ratio with a 1:1:1 mapping between names and pieces of data. So the file is named aqua02, the function is aqua02, and then the actual data is called aqua.svg, or aqu. whatever. That's intentional so that, you know, if we want to come back to this code in a year and we want to figure out how the heck did we get that graphic, what function made that graphic, we have an easy way to connect those dots. Okay, so the next thing is, before we start adding the main code, here's the cutting file, right? And so we're going to add that boilerplate for the cutting file, right? So we're going to go in here, and this is going to be AQU, right? AQU? Aquarius? AQU, yes. So the first three letters of Aquarius are going to be put in here, right? And then we're going to change anything, anywhere where it says Capricorn, we're just going to change that to Aquarius and be very careful that we spell that correctly. So Aquarius. Aquarius. Okay. So we'll change that to Aquarius. Right? And then this section itself is going to be called Aquarius code, right? So AQUARIUS. I can't spell, so I have to actually be careful about this. Okay. Okay, so now that we have this, I'm thinking, can we just take care of the other symbol as well? Like write all the boilerplate? Let's not do that. Let's do it one at a time so we can make one video for each kind of thing we're working on here. So let's close this, and let's put this debug back on. Okay, and then we're going to go find this file, right? We're going to open it in OpenSCAD. so that we can see what we have here, right? So right now we just have this wheel pattern. We're going to put the symbol inside that wheel pattern. And to do that, we're going to need a function code for that. So in here, we're going to say Aquarius. So Aquarius code. Aquarius code. I can't spell, so I got to be careful here. I hear in some languages, when you ask how to spell something, people just pronounce it for you because the language is, you call it, is so, it's so perfectly phonetic that you don't have to do this, right? So sometimes you might hear me say something, I'll say it in a phonetic way. Instead of how it's pronounced, I'll actually say it phonetically so I can try to type the right keys. So this would be Aquarius, maybe, right? If we wanted to pronounce that perfectly phonetically in order to remember how to spell it. So Aquarius. Okay, SBC. Okay, so we want to stub this in, and then we want to call it right away, so that we can see what we have so far. Well, what we have so far is absolutely nothing, but we just want to make sure that we didn't impose any kind of syntax error. So now we have to think about, well, how long do these lines need to be? And I have no clue how long these lines should be. I'm thinking maybe 2 inches? I don't know, it's just a guess. So what we're going to do here is we're going to go up to here, right? And we're going to create a section for Aquarius symbol. So Aquarius symbol consts. And my guess is that Aquarius, let's just call it implen, and just call it 2 for now. The idea, and why we only have length, and we're not calling it like wavelength or some other length, is if there's not going to be any other length variable for the Aquarius symbol, then we don't want to be overly verbose, right? So we want to be we want to just be as specific as, no more specific than what is required to uniquely identify the data we're working with, right? To avoid being overly verbose. So, wave try side length, right? It would be like, this would be like the more specific of what we're talking about, right? But this is harder because I don't know what does anyone know what a wave try side length is? Nobody knows what that is, right? But we know that this, so with naming things, right? There's no fanciful name you can give something that's actually going to tell you what something is, right? This is just like some descriptor that I just made up off the cusp, right? So if we want names that have, like, are data-oriented and actually tell us exactly what we're looking at, then we have to be a little bit more ugly, I guess, right? So ZOT is the namespace. Okay, that tells us something. Aquarius. Aquarius is a subnamespace, so it's for the Aquarius symbol, right? And then imp is for imperial and len is for length, right? So we know it's an imperial unit, and we know it's a length, and we know it's for the Aquarius symbol, and we know it's for this zot.scad library, right? So all the parts here have a very formalized grammar, and that is intentional. Okay, so with that, we can go down here, right, into the code, and we can just say, hey, length equals, we can't really say length because length is a keyword, so we're going to say imperial length equals that, right? And then we're going to just say vcarve inch line, right? And we're going to say SBC, and then we're going to take a thickness variable, and then we need a point, I'll just call it point 1 and point 2. Let's just not worry too much about that. So for point 1, where's point 1 going to be? I don't know. Point 1, we can just make, you know, at 0, 0 for now. And then point 2 can be, we can try like 45 degrees, right? So 45 degrees, so 45 degrees would be the cos of some type of angle, right? So let's try 45, right? Times some type of scalar, which is going to be the scalar here, right? Okay, and then the sine of 45 degrees, okay, is times the imp length, right? So, assuming that we start off at the origin P1, right? Okay, so we got something good there. Let's just give that a run and see if we've screwed up anything. Ignoring variable thickness. So we have to make a thickness variable. So let's just steal this, because this is... we use this everywhere, right? So let's just steal the thickness variable here. And the thickness is also an imperial, but I use it so often everywhere else, I've just been keeping it very short. Very shorthand. And let's give that a shot. F4. Okay, cool. So we got this thing. That needs some work. In fact, it looks like the line for the Aquarius symbol isn't quite a 45. It's like a maybe a 30 degree might make more sense. So let's try a 30 degree line. Okay, yeah, that could be more workable. So the next thing is this length, right? We're kind of guessing at the length, and I think that's too far. That length for this, I'm thinking just 1, and then F4. Something like that. Okay, so now the next part is to kind of put this together in a very procedural way where we can easily move things around. So I'm thinking for this, we just say we go 0 and then 0 minus some number of inches, so like, I don't know, 3, we can just guess for now, and F4, right, and we just move it. Right now I did that wrong because I get my X and Y axes mixed up sometimes. So this is 0 here, and then this is over here. Okay, cool. So now let's just align that nicely. Okay, look at this again. So F4, way too far back, right? So let's go like 2, F4. Okay, so that could work with what we're doing here. Now I kind of feel like maybe the line needs to be more, what do you call it? Steeper, but let's just try to go with this and try to get, try to parametrically kind of model this out. So for a point 3, we're going to start off at point 2, right? Point 3, we'll start off at point 2, and then instead of going, 30 degrees, we have to go 30 minus 90, right? Or 30 minus... well, it's not really... We want the angle to be... we want the correct angle in relationship to... what? If we're going at 30 degrees, then we want to go back down at... If we're going up by that amount, we want to go down by the same amount, right? So... do we want to just put a 180 on that? Is that a 180? What is that? So here's what I'm thinking here, right? So if we're going... if we went up like this by a certain amount, right? If we go up by a certain amount, eventually we want to come down at the exact same angle, right? So how do we calculate that in a dynamic way, right? How do we calculate, right? If this is 30 degrees, if this is 30 degrees up, then what's this, right? So that's 30 degrees. This is, what is this right here? And I'm not sure what that is. So we have to take some time to think about that. And it should be pretty obvious. It's like a reflection angle, alright? Some type of reflection. But let's just put this here for a second so we can contemplate it. And is this so it's not a perpendicular, right? It's not perpendicular. It's more like it's kind of mirrored on here, right? It's mirrored along here, right? It's the angle of incidence and angle of reflection, right? That's what's kind of happening here. So I don't know how you get that. Find reflection angle. So how do we calculate a reflection angle, right? So, right, like if this, so we know the surface. So if we know the surface normal, incident ray, reflected ray. So let's look at this. Angle of reflection in physics. So we can use the normal of the surface, right? So the normal of this surface here, right, is the surface normal here is a this surface normal, if we want to look at it like that, is if this is 90, this is 180, this is 270, right? So this is a 270 degree right, so that's a 270 degree surface normal there, right? And so there's probably like some dot product calculations or something that I'm not super familiar with, but this would be good for working on rendering engine code too, so this could apply to rendering engine stuff, so let's kind of figure this out. Let's close this, or not. Continue to cite. Okay, angle of incidence and angle, so there's the... So here's the ray, and there's the reflection. So theta 1 and theta 2 are equivalent to each other, I'm guessing, right? So around the angle relative to the surface normal is always the same, right? With the incident and the reflection, right? So I want to calculate the reflection using surface normal. Calculate reflection using surface normal. And I really don't want to make it this complicated, but if we can figure that out, then we're good, right? Okay, n must be normalized. So A, B. So A goes in, B goes out. Okay. Here's n. Yeah, so this is kind of what I'm going for, incident ray. In case you want to rotate about the y-axis, you can use the following instead. This is mostly useful for computer graphics applications. Note that D is assumed to be pointing outward in the equation below, ignoring the direction of D in the picture below, and N needs to be normalized. So N needs to be normalized. Okay, so these are normalized. They're not going to be angles, right? They're going to be so let's take that. So 2 times D dot N. Where's D in here? I don't see D in here. Incident ray. I don't know. I don't see where that is. Are there any images that'll just have the correct thing? Okay, let's just read some stuff and we'll eventually figure it out, right? Okay. So, Maxwell's equation can be used to derive the laws of reflection and refraction, which tell us how light waves behave at the boundary between two media with different indices of refraction. Okay? Reflection. Reflection is the abrupt change in the direction of propagation of a wave that strikes the boundary between two different media. At least some part of the incoming wave remains in the same medium. Assume the incoming light ray makes an angle theta I with the normal of the plane tangent to the boundary. Then the reflected ray makes an angle theta R with this normal and lies in the same plane as the incident ray and the normal. Law of reflection. Theta I equals theta R. Okay, got it. And so you can see this in the diagram, right? Theta I and theta R. So it's the angle between this incident ray and the normal and the reflected ray and the normal. Those angles are identical to each other. So I understand that. I understand that aspect. Specular reflection occurs at smooth plane boundaries. Then the plane tangent to the boundary is the boundary itself. Reflection at rough, irregular boundaries is diffuse reflection. The smooth surface of a mirror reflects light specularly, while the rough surface of a wall reflects light diffusely. The reflectivity, or reflectance, of a surface material is the fraction of energy of the oncoming wave that is reflected by it. The reflectivity of a mirror is close to 1. And so I actually was reading an article on, like, everything is specular. So a lot of times you only think of, like, very shiny materials as having a specular channel, but it turns out, like, even materials like cotton or wool can be up to, like, 50% specular. Like, it's crazy. In terms of, like, how much... So there's specular, which is what's going to be emitted, like, bouncing off, and then there's going to be... and then there's what's going to be absorbed, right? There's light that's absorbed, and there's a light that's kind of given out, right? When you're talking about rendering, which is different than how people... I'm talking about physically based rendering specularity, not the old, like, Phong mode specularity. It's slightly different. Actually, let me find that for a second. Everything is specular. Okay, I know that's a thing, but everything is specular. How about everything is shiny? Yeah, there we go. So this thing right here, everything is... So this blog post here, like, has some good stuff here. Or they're talking about, like, taking, you know, like, looking at different fabrics with, like, I believe, like, a polarized camera of some sort to figure things out here, and a polarized lens of some sort, and, you know, the main image, the diffuse, and the specular, and look how the diffuse and the specular both have, like, a lot going on here. So, cardboard's shiny. Main, diffuse, specular. So maybe I don't have my definitions for diffuse and specular correct here in terms of physically based rendering, because these are both emitted light, right? Anyways, this is good to read over. Yeah, this is really good stuff. Anyways, that's a tangent, though. We're trying to figure out how to write this formula. Specular reflection occurs at smooth plane boundaries. Then the plane tangent to the boundary is the boundary itself. Reflection at rough, irregular boundaries is diffuse reflection. The smooth surface of a mirror reflects light specularly, while the rough surface of a wall reflects light diffusely. The reflectivity, or reflectance, of a surface material is the fraction of energy of the oncoming wave that is reflected by it. The reflectivity of a mirror is close to 1. Refraction. Okay. Refraction is the change in direction of propagation of a wave when the wave passes from one medium unto another and changes its speed. Light waves are refracted when crossing the boundary from one transparent medium into another because the speed of light is different in different media. Assume that light waves encounter the plane surface of a piece of glass after traveling initially through air, as shown in the figure to the right. What happens to the waves as they pass into the glass and continue to travel through the glass? The speed of light in glass or water is less than the speed of light in vacuum or air. The speed of light in a given substance is v equals c divided by n, where n is the index of refraction of the substance. Typical values for the index of refraction of glass are between 1.5 and 1.6, so the speed of light in glass is approximately 2/3 the speed of light in air. 2/3. Okay, so it's slower. Okay. The distance between the wave fronts will therefore be shorter in the glass than in air, since the waves travel in smaller distance per period. Okay. If f is the frequency of the wave and t equals 1 divided by f is the period, i.e. the time interval between successive crests passing at a fixed point in space, then, what is that, lambda? I think that's lambda. So this is a little bit more detail than I need. This is lambda. Okay, yeah. And lambda is that like a, what's the difference between lambda and delta? Lambda linear algebra. So what is lambda in linear algebra? What does lambda mean in linear algebra? Like, what does that mean? I don't know. But we'll probably have to figure that out, right? It's an eigenvalue. If you have an n by n matrix A and a vector x, then there's a special type of equation, ax equals lambda x, where lambda is a real number, not a matrix. It means you take a matrix, let it act on a vector, and it returns the vector with a scalar number in front. Equivalently, we have ax equals lambda ix, since ix equals x, which means a minus lambda I, the condition, yeah, so I don't know. Determinant. These eigenvalues have really important applications in physics. Okay, so I'm just going to have to, like, watch more stuff on mathematics. Now consider wavefronts and their corresponding light rays approaching the surface at an angle. Do we want to read all this? Because I think we're not going to get very far reading this. I guess we should try to, like, read stuff we don't understand, and then if we do it all the time, maybe we'll understand. I don't know. We can see that the rays will bend refraction. Okay, refraction is the change in direction of propagation of a wave when the wave passes from one medium into another and changes its speed. Light waves are refracted when crossing the boundary from one transparent medium into another because the speed of light is different in different media. Assume that light waves encounter the plane surface of a piece of glass after traveling initially through air as shown in the figure to the right. What happens to the waves as they pass through the glass and continue to travel through the glass? The speed of light in glass or water is less than the speed of light in vacuum or air. The speed of light in a given substance is v equals c divided by n, where n is the index of refraction of the substance. Typical values for the index of refraction of glass are between 1.5 and 1.6, so the speed of light in glass is approximately 2/3 the speed of light in air. The distance between wave fronts will therefore be shorter in the glass than in the air, since the waves travel a smaller distance per period t. Okay? If f is the frequency of the wave and t equals 1 divided by f is the period, i.e. the time interval between successive crests passing a fixed point in space, then lambda subscript 1 equals v1t equals ct divided by n1, and lambda 2 equals v2t equals ct divided by n2, or lambda 1 divided by lambda 2 equals n2 divided by n1. A whole bunch of stuff I can't comprehend. Now consider the wavefronts and their corresponding light rays approaching the surface at an angle. Okay, we can see that the rays will bend as the wave passes from air to gas. The bending occurs because the wavefronts do not travel as far in one cycle in the glass as they do in air. As the diagram shows, the wave front halfway into the glass travels a smaller distance in glass than it does in the air, causing it to bend in the middle. Thus, the ray, which is perpendicular to the wavefront, also bends. The situation is like a marching band marching into a muddy field at an angle into the edge of the field. The rows bend as the speed of the marchers is reduced by the mud. The amount of bending depends on the angle of incidence and the indices of refraction of glass and air, which determines the change in speed. From the figures, we can see that lambda 1 divided by lambda 2 equals sine theta 1 divided by sine theta 2, but lambda 1 divided by lambda 2 equals n2 divided by n1, therefore n2 divided by n1 equals sin theta 1 divided by sin theta 2, or n1 sin theta 1 equals n2 sin theta 2. So a whole bunch of stuff I don't get. This is Snell's law, or the law of refraction, right? Okay. So ni equals sin I equals nt sin t. Okay. So we have an angle I and an angle t, and there's equivalence between them, right? So, okay. Angle of incidence, angle of refraction, normal. Okay, got it. So we're talking about, when we're talking about refraction, we're talking about rather than bouncing off, we're talking about going through the surface, and there's an angle change, right? And so this normal is perpendicular to the surface we're piercing, and this angle kind of changes when it hits the water, right? Okay, got it. So I kind of understand this diagram. It's just that the mathematical explanations are kind of complicated. Snell's law diagrams. Snell's refraction diagrams, reflection diagrams. Okay, so this is good information. It's just not what I want for right now. It's like too in depth. I just want to calculate how we bounce light. When light passes from one transparent medium into another, the rays are bent towards the surface normal. If the speed of light is smaller on the second medium than in the first, the rays are bent away from this normal. If the speed of light in the second medium is greater than the first, the rays are bent away from this normal if the speed of light in the second medium is greater than the first. Okay. The rays are bent towards the surface normal if the speed of light is smaller in the second medium than the first. The picture on the right shows a light wave incident on a slab of glass. Okay. One part of the wave is reflected, and another part is refracted as it passes into the glass. The rays are bent towards the normal. At the second interface, from glass into air, the light passes into the air as refracted again. The rays are now bent away from the normal. Okay, so, reflectance and transmittance. At a boundary between two transparent media, light is partially reflected and partially refracted. The ratio of reflected intensity to the incident intensity is called the reflectance R, and the ratio of the transmitted intensity to the incident intensity is called the transmittance T. Energy conservation requires that R plus T equals 1 if there is no absorption. R and T depend on the indices of refraction of the so if there's no absorption, so that means that R plus T equals 1 if there's no absorption, but it should never exceed 1. So if there's absorption, then R plus T would be less than 1, but absolutely by no matter what's going on, it shouldn't be greater than 1. If I understand this correctly. Okay, so R and T depend on the indices of refraction of the two media, N1 and N2, the angle of incidence, θ1, and the polarization of the incident light. We distinguish between P polarization and S polarization. Let the plane of incidence contain the normal to the boundary and the incident wave vector K1. The electric field vector E1 is perpendicular to K1. If we choose our coordinate system as shown on the right, then plane of incidence is the xz plane, and E1 may be written as E1 equals EP plus ES. EP lays on the plane on the xz plane, and ES is perpendicular to the xz plane, i.e. it points in the plus minus y direction. The electric field of the incident light is a linear superposition of P minus and S minus polarized fields. Way too much information for me. But I do just want to read this whole thing because it's not too long. For polarized light, we have R equals the absolute value of R12P power of 2, where R12P is the Fresnel reflection coefficient. For P polarization, we have R12P equals tan θ1 minus θ2 divided by tan θ1 plus θ2. For S-polarized light, we have R equals the absolute value of R12S power of 2, where R12S is the Fresnel reflection coefficient. For S-polarization, we have R12S equals sine θ1 minus θ2 divided by sine θ1 plus θ2. Hold on. Oh, okay, yeah. So the sine of the sine of the difference of the thetas divided by the sine of the addition of the thetas. Okay. For a graph of the reflectance R for S and P polarized light as a function of N1, N2, and theta 1, download this Excel spreadsheet. If theta 1 and theta 2, N divided by 2, then tan theta 1 plus theta 2 equals infinite, and R12P equals 0. If light is reflected, it will have S polarization. The incident angle at which this happens is called the Brewster angle, theta B. We then have N1 theta 0B, some kind of like yield symbol. Oh no, hold on, my monitor's just dirty. Equals N subscript 2 sine N divided by 2 minus theta B equals N subscript 2 cos theta subscript B. Tan theta B equals N subscript 2 divided by N subscript 1. Polarized light can thus be obtained via reflection. Anyways, too much information. Too much information for me. Yeah. Too much info. So really what we're looking at here is pretty concise. It's just that I don't have the background knowledge for this. So, okay. So, it's covering water reflection, it's covering glass reflection. Okay, so let's kind of like look at some more stuff, right? We know that we just want to calculate this, right? We want this kind of mirror reflection, right? And that's all we want to do, right? We just want to figure out how to do this, right? And it should just be like some dot product. And I would like to figure out how to do it with like just degrees, but let's not worry about degrees. Okay, Chapter 10, Mirror Reflection. 10.1, the physics of mirror reflection. Like refraction, mirror reflection is a phenomenon that occurs at the boundary between two substances. In both cases, a portion of a light ray's energy is sent in a new direction when that ray hits a point on the boundary. Unlike refraction, mirror reflection causes light to bend back into the substance from which it came, instead of bending along the path into the new substance. Mirror reflection is also mathematically much simpler than refraction. The refractive indices of two substances affect the amount of reflected light, but they have nothing to do with the reflected light's direction. Yeah, so that's the thing, right? So the index of refraction for refraction will also change the angle, but with reflection, the angle is always the same. The angle is always consistent, but it's just the amount of light that gets bounced back here, right? So there might be 100% light hitting here, and then maybe 50% of the light bounces back, or 50%, 25%, some type of percentage of light bounces back, but the angle is very predictable. Okay, so the refractive indices of two substances affect the amount of reflected light, but they have nothing to do with the reflected light's direction. Light always reflects at the same angle as it arrived, as measured from a line perpendicular to the surface. Just as we saw with refraction, the selected ray lies in the same plane as both the incident ray and the perpendicular line, only on the opposite side of the perpendicular line as the incident ray, right? So you have this surface, you have the surface normal n. The surface normal is being perpendicular to the surface, and this angle here, this theta angle here, and this theta angle here, they're both exactly the same, right? So we have this input and we have this output ray. So let's keep on reading here. Figure 10.1, the incident ray E strikes the boundary between two substances at point P. The ray reflects the direction R. The ray reflects in the direction R. The rays E and R both extend the same angle theta from the surfaces perpendicular. Okay. Two kinds of reflection, same vectors. Okay, in Chapter 7 we learned that this ray tracer source code models mirror reflection at the sum of two separate kinds of reflection, glossy reflection and refractive reflection. To recap, Glossy reflection belongs to an imaginary coating on an object's surface. Refractive reflection, however, is determined by the refractive indices of substances on the opposite sides of their common boundary. Glossy reflection may vary across an object's surface, but is equal in intensity regardless of the angle of the light's incidence. Refractive reflection is more intense for light rays that arrive at a larger angle from the perpendicular. Glossy reflection can impart a color bias into reflected light, but refractive reflection bounces red, green, and blue light equally. Okay. A little bit more information than I need. I just want to calculate some angles here, but this is good information for when I work on some more rendering engine code. In spite of all these differences, they share an important geometrical trait. In both kinds of mirror reflection, the same incident ray E results in a reflected ray traveling in exactly the same outgoing direction R, as depicted in Figure 10.1. For this reason, the ray tracer code calculates the intensities and colors of glossy reflection and refractive reflection separately, but adds them together and calculates their common direction R using a single member function, calculate reflection. So some type of composite ray that is computed from merging reflection and refraction together is kind of what I read there. Okay, 10.3, deriving the vector formula. Okay, so we got this E and R, and we got this B. Okay, and they're denoting, I think these arrows are denoting what direction these vectors are pointing in. So we're not really looking at line segments. I think we're supposed to be looking at vectors, right? So these lines here in this diagram are representing vectors. And little arrows are telling me what direction they're pointing in, I think. I'm pretty sure, right? Because these aren't congruency lines, right? These are just direction lines, I believe. Vectors used in the derivation of the reflection formula. Okay. We now consider the problem of calculating the mirror reflection vector R given the incident light ray vector E and the surface normal vector N. The first step is to break E into the sum of two vectors, A and B. Okay, so where's E? Okay, so there's E, and we're breaking it into vectors A and B. Oh, got it, yeah. So we're taking the X and Y, right? We're taking the X and Y, and we're just breaking it into A and B. And these vectors are perpendicular to... These vectors are... we're just separating the components, the X and Y components. So these are vectors, the A and B vectors are aligned to our coordinate system, I'm assuming. The first step is to break E into the sum of vectors A, B, such that A is parallel to the reflective surface, and B is perpendicular to it. Okay, so it's not in terms of our coordinate system, it's in terms of the surface normal. Okay. As depicted in Figure 10.2, reflected light bounces away from the surface at the same angle as the incident light, so the angle between E and B is the same as the angle between R and B. Two symmetric right triangles appear, ABE and ABR. So we got ABE and ABR. ABE, ABR. Got ya. So I'm not sure why they list the sides in that order, where we go clockwise and then counterclockwise. I think it's because we're listing off the sides in terms of which sides have the identical lengths, since these triangles are symmetrical. We can now see from Figure 10.2 that the following two vector equations must be true. Initially, the second equation might be easier to understand, rewritten B plus R equals A. So B plus R equals A. So B plus R equals A. Okay, it's because we go B, if we go from here, if this is at 0, 0, and we add B, and then we add R, we end up over here, right? And so 0, 0 to here is a certain length, right? So 0, yeah, okay, so I get how we're saying B plus R equals A, right? So B plus R gives us, if this is 0, 0, we add B, we add R, right? And now we have a certain length only on the x-axis. Okay, yeah, makes sense to me, okay. B plus R equals A. I'm satisfied with this. It's a little bit confusing because I'm not super familiar with linear algebra, but I get it. Okay. But the form below is more useful to the upcoming discussion. So E equals A plus B. Okay, so E, right here, equals A plus B. So if we go A plus B, we get E, right? If this is 0, 0, right? This is the final point here, right, is the magnitude of E. If you go A plus B, right, and also the coordinate. Okay, I get it. Okay, cool. So R equals A minus B. Okay. So R equals A minus B. So if we go A and then we go minus B, that's kind of confusing, but A and then minus B, I'm a little bit confused there. I get A plus B, that makes sense. But A minus B, I don't quite get. Because that looks to me... well, let's look at this. So I could see B plus A is what I'm assuming R would be. B plus A. I don't understand the subtraction here. I get this A plus B, right? Because A plus B, or A plus B from here. A minus B though. Yeah, I don't quite get that. Let's just keep on going. We can find the perpendicular vector of B by noting that since it is the component of E perpendicular to the surface, its magnitude must be equal to the dot product of E and the surface normal vector N. Likewise, B must point in either the same direction as N or the opposite direction, negative N, regardless of the orientation of the N, i.e. whether the reflection is occurring on the outside surface or the inside surface of an instance of solid object. The following equation works. B equals E dot product N times N. So dot product of the normal times the normal. I don't understand why I have to why that works, but okay. To convince you that this equation works in both cases, consider each case separately. If the normal points in the opposite direction as B, or upward as seen in figure 10.2, then E dot product N is a negative number, and multiplying any vector by a negative number results in another vector pointing in the opposite direction. Thus, E dot product N times N points in the same direction as B. Alternatively, if N points in the same direction as B, downward as seen in the figure, the dot product is a positive number, and therefore E dot product N times N still points in the same direction as B. So we're getting into stuff I don't understand, but let's just keep on reading. We're going to keep on reading stuff until we figure out the angle, the angle kind of formula here. And we might already have read it and just don't know what we're looking at yet. Okay. To convince you that this equation works in both cases, consider each case separately. We now substitute the value B into the equations for E and R. So E equals A plus E dot product N times N. R equals A minus E times dot product N times N. Subtracting the first equation from the second results in A canceling out, and adding E to both sides of this new equation results in the following formula for the reflected ray. R equals E minus 2 E dot product N times N. This is exactly what we wanted. We now know how to calculate R using only E and N. So R using only E and N, which is what we want to do. And so this is the formula. This is the formula that I actually want. So I'm going to make a note of this. Cosine kitty reflection. So, pick okay. So this formula is R equals E minus 2E dot can we steal the dot product symbol? Unicode dot product symbol. In Unicode, so this is the dot product operator. Okay, so the dot product is, so dot product symbol. I'm making some notes here. So the only problem is that this symbol is very, let's close this. So let's write this formula out in a way that's going to be kind of more comprehensible in terms of code. So this formula really what it is it's like it's input angle R, input angle R equals output angle E, right? No, output angle is E, right? No, the input angle is E, the output angle is R. Okay. So output angle R equals the input angle E minus 2 times and these aren't really angles, right? They're vectors, right? So let's just say V. Okay, so Okay, and this part in here, this is a dot product. Okay, so really quick, what I wrote down here is this formula here is kind of what it is, right? So VR is vector R, output angle. Okay, VE is going to be vector E, input angle. And then SN is going to be surface normal. Must be normalized. Right, so that normal must be normalized for this to work. So we might want to codify this, right? So VR, right? And just say, if you type VR, that's figure out food. Okay, hold on. Okay. Okay, so VR, vector R, output angle, and reflection formula. Right? And then let's steal this for a second and say, well, what's VE here? So VE is vector E, and that's the input. Okay. And then if we just do VR, then we're just going to say VR and if we do VE, we're going to do VE. And if we do something kind of close, we'll fix it, right? So we'll do like a VE or a VE, or VE, or VE. Any of these? Okay, sure, why not VE? VE. Okay, so any of these we'll just correct it as VE, right? So lowercase v, capital E, which is kind of different from how I do a lot of variables. So we have the vector E, and then we have the vector R, right? So vector R, vector R, vector R, and vector R, okay? And vector R, we'll do a little correction there, okay? And also capital V, lowercase r, capital V, lowercase, okay, like that. Okay, so I have to take a break and go upstairs really quick. But let's make a note of this website that we're reading right now, right? So we're going to keep on reading this, and then eventually we're going to figure out how to do this. So this is the cosine kitty formula. So we need coskit URL. So coskit URL, right? So cosine kitty URL, right? And we'll keep on kind of reading and trying to figure out this reflection stuff so that we can make this angle. This angle goes up, and we are kind of assuming a surface normal here, and we want to go back down, right? We want the reflection to be perpendicular to this x-axis here, right? In order to parametrically kind of draw this in a way that kind of makes sense. So I will be right back. I'm going to start a break timer. Break timer. Okay. Just want to do 40 more. Six, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. So I got 20 more, so that's 60 total. I don't know why my time doesn't say that, but I'm gonna stop the break timer here. And today, yeah, we've done 60 now. Okay, so this thing here, we did 20 more, so we're at like 400. Okay. So let's kind of keep on reading things and try to figure out what the hell we're doing. Okay, so let's read more of that article, right? So this is basically what we're saying is the formula. Now the thing is that these are vectors, right? These aren't angles. This is exactly what we wanted. Now we know how to calculate R using only E and I, right? Okay. Okay. So we're just gonna go with that and see if that's what we need. And let's hope that we don't have to read any more of this, and that's all we need to do. So what I'm thinking is we make a function here that can calculate that for us. So I'm thinking we have a function that how do we even want to do this? So what's the dot product, right? So so first of all, let's just go in here. Let's just create a formula in here, right? So let's say formula functions. All right, let's just create a dot in here. I know there's already a dot function that's built in, but let's try to write everything from scratch so that we can assure ourselves that we understand the formula well, right? So function SBF shotbot functions dot. So SBF dot, okay, and we'll have an A and a B equals, no squiggly brackets for a function like this, and we have something like this, but this is not a, this is a dot 2D, D2D, so dot product 2D, right? So dot product 2D, and that means we don't need a z-axis, right? We can just do this, right? So it looks like all dot product is we're taking the components, the same component values, and we're just multiplying it together. So dot is just a, well, we're multiplying them together and then we're adding them all together. So this ax bx would be this. It would be this is ax times bx, right? So that's right. So this is ax times bx, right? Plus, and then this is ay by, right? So ay times by, right? So it's the ones, and then we add it together. So this is going to be a dot y times b dot y. So we're just putting that comment there so we know exactly what that is, right? So now let's go F4, make sure that in the introduction of that formula didn't kind of screw us over here. Okay, so with that, the next question is, how do we do the reflection stuff? So, so we're thinking that, you know, function SBF reflect 2D. So reflect 2D, and for that we're going to have a, we're going to need a angle, incident angle, and we're going to need a normal, right? So En, right? So I don't know why they're called E and N in those formulas, but that could actually be important because that might just be a standard for naming vectors for reflection formulas. So just doing this might be within our best interest. Okay, so within here, E and N. So this is reflection 2D, R2D, dot product 2D, D2D, right? Okay, so within here, what's the formula? Well, the formula is the vector E, well, first of all, we're taking a vector, right? So the output actually needs to be a vector. So the output of the other one was a scalar. This is a scalar output, but this is an output vector, right? Because we take a vector in, and then we have a vector out. So when we're saying, you know, the E0, right, minus 2 times the dot SBF shotbot functions dot 2D, and it's the dot of E in the normal. So we take E in the normal, and then we times it by the normal, right? So let's just call this VE for vector E, and SN for the surface normal. Let's be a little bit more verbose. So vector E, and then this is also vector E, and this is the surface normal, and this is the surface normal, right? So surface normal. Right, and now we might want to break this apart, right? So break this apart a little bit so that we can kind of read it a little bit better. So vector E, input angle, and then SN, surface normal, right? Surface normal. Vector E, surface normal. And this is the formula, right? And we have to recalculate some stuff because of the functional nature of the language. So VE1, right? Because we see that in the formula we take a vector and we minus kind of this stuff here, right? So we got to go 2 times SBF dot product 2D vector E surface normal, and then times the surface normal, right? So that's what we think the output of this is. So let's go F4, make sure we haven't introduced any syntax mistakes, and then let's try that out. So we have this reflection thing, right? So a reflection function, and we're hoping that that reflection function works properly. So this is going to be in terms of vectors, though, right? So we want to go from point 1 to point 2, right? And so if we're trying to get the reflection, so vector reflection equals, right? Okay, so R is for reflection. I don't know what E is for incident. I don't know. So vector reflection equals, and we're going to say P12 or vector 1, 2, right? Vector 1 to 2. So vector 1, 2, and then surface normal. Okay, and the surface normal is pretty easy. The surface normal just equals well, if this is going from here, it's going to be bouncing off of something up here. So the surface normal is going to be pointing downward. So it's going to be 0 on the x and then 0 minus 1 surface normal there. Okay. And for the vector 1, 2, vector 1, 2, SBF so make vector, actually let's not do that. Okay, so for this, it's to go from 1 to 2, it's 0.1. And we want to look at the x components first. So to go from 0.1 to 2, we have to go 0.2, the bigger, minus the smaller, right? So this is the vector, right? So 0.2 minus 0.1. Right? So this is P1 to P2, x-axis, right? Because we're using the zeros. And then this is P2, this is P1 to P2, y-axis, here. Okay, so with that, we have this vector here. Let's just run that, make sure it doesn't crash on us. So F4, okay, cool. And then we have this reflection vector that we think is correct. We don't know if it's correct yet. But if it's correct, then what we can do is 0.1, 0.2, .3 isn't being used here, right? This is just a guess, right? So 0.3, we're thinking is without using any kind of stuff here, we should just be able to take this, we should take 0.2 plus the vector of reflection, right, on this axis, and then the vector of reflection on the other axis, right? And if we do that, then if we make another line, right, if we make another line, and this one, instead of 0.1 to 0.2, it's 0.2 to 0.3, give that a shot. Well, that roughly may be in the correct location, except for, so first of all, how the hell So it looks like 0.3 or something. Something's gone wrong with this math, right? Because we see that right here, it's like, nope, it's nopin', right? So if we go over here, F4 for a second. That's interesting that it goes from here to here. So this third parameter, I'm going to guess, has some invalid values in it, right? So, that vector should not be zeroed out by any means. It should have a non-zero value for both of them. So if not VR or VR echo bad vector VR. Okay, so let's just kind of do some hackish error checking here, because we're thinking that our formula is failing us horribly right now. VR.x, and this is VR.y, right? Okay, so let's take a look at that and see if maybe we get a little message in here. Bad vector VRX, bad vector VRY. So this VR is totally screwing us over, right? It's like, oh, you think you want to do this stuff? Screw you, right? And so the question is why? Why is that the case? Well, we have this vector input thing, and then the output is supposedly supposed to be a tuple, right? And we can see a mistake here. Well, no, that's not a mistake. A and B. Well, is the surface normal correct? The surface normal, that's also a tuple, okay. So is this wrong by any chance? So this gets us a scalar times... Oh, wait, that's what's wrong. So when we times by the surface normal, right, we're just multiplying its component-wise. So this is surface normal 0, and this is surface normal 1, right? Okay, so now if we do this and go F4... Oh, hey, there we go. Nice. So that looks like that might actually be correct. So if we comment this out, right, and we look at that for a second, F4. That looks kind of correct. That looks like the correct math. Excellent. Now the next thing is... well, what about like doing the like doing this with angles, right? Because we have... Let's not worry too much about angles. I think we've kind of done enough where it's like, I'm sick of this. Let's just get it. Let's just get this simple. Right? This shouldn't be that hard, right? So we're just gonna go boom, 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 right? So we're gonna go. We want to add more of these vectors, right? So, we have. This is the vector here, right? So. If we think about it, this is the reflection vector. VE equals, right? We could extract this, right? So this is the initial vector is VE this, and then it's VE that, VE that. Okay, so let's just do it. We're doing a little bit of refactoring, and it's a ugly mess, but oh well, we'll worry about that later. Okay, so now that we have both these vectors, right? P3 equals this, right? What about P4? Well, to get P4, we're just going to start off at P3, and we're going to do the other vector, right? So we did this up, down, right? Duplicate that. So we're going to go 3 to 4 now. F4. Excellent. And we'll just keep on doing that, right? So now, we have... We'll do the reflection vector again, right? So V5 starts out at V4. And let's duplicate this. So we went 3 to 4, and now we're going to go 4 to 5. Okay, F4. Okay, so now we got this little M thing, but it doesn't. We don't want it to look like an M. So, hey, how's it going? Or what am I doing here? Yeah, I'm parametrically drawing zodiac signs. That's what I'm doing here. Yeah. So, okay. So let's do this one more time. So we need like one more piece. So this is going to be P6. We start off with from point 4, and we use this vector here. And let's just duplicate this line, right? So we're going to go 5 to 6 now. 5 to 6. And F4. Okay, so now we have kind of the basic kind of zodiac symbol kind of thing we need. But we need 2 lines, first of all. We need to position the lines a little bit better, but one thing at a time. So let's take all of this stuff we have here, and I'm thinking we just have to do a little translation. So integer y SBC for the shopbot constants, and go maybe like 0.5 inches up. Actually, no, 0.25 I'm thinking, because it's going to have to go up and down. Because we're going to have 2 of these lines for this zodiac symbol, because this was the Aquarius symbol. Okay, so if we look at this, and then we just copy-paste, right? We're not going to worry too much about the fact that this is dirty as heck. Just get it working, right? So if we do that, too close together. So maybe the 0.5 is what we want to go with here. Okay, so something like that ain't bad, right? It's like a little bit, a little bit close together. I don't know. I think that's good. So now the last thing is we want to get rid of the rounding on the ends. So for these last things, we can do a 0 to get rid of the rounding on the ends, on the tips. Well, F4. Okay. So if we run that, right, so now we got rid of the rounding there. And I'm thinking we want to get rid of the rounding on the beginning as well. So to get rid of the rounding on the beginning, there we go. So now we have kind of this thing here. I like that. That's pretty okay. It needs to be kind of translated more into the center-ish, right? Because this is not quite where it needs to be. Now for that, we're not gonna, well, we could try to figure that out, right? So, we started off with something on the line, right? So we might as well try like IY SBC 0 minus 0.5. I don't know. But let's try to center it right here anyways. Let's just try to... Okay, so that's a little bit too much. That's not quite good. 0.25 maybe. Something like that. Yeah, I like how it kind of tangents the line there. Right, the crest of this bottom thing here, the crest of the bottom squiggle hits the x-axis, and then the valley of the top squiggle hits the x-axis. So I like how that feels very centered. So the next thing is that this needs to be a little bit more centered on the x-axis. So I'm thinking that we just need to get this plunge line kind of between this point and that point, right? And I don't know exactly how we're going to do that. I think we'll just kind of guess and check, right? So SBC 0 minus 0.25. First we'll just try 0.25 and then we'll go from there, right? And if we look at that, F4, see how that looks. It looks a little bit too far to me. So it's too far back. So 0.20 and F4. Try that out. That looks pretty good. We could try 0.18. See how that looks for a second. F4. Didn't really notice much of a difference. I'm going to go with that. I'm going to say, hey, that looks pretty good. Right? And we'll ship that. We'll ship that. So, okay. So now that we have that, let's package it up, right? So the first thing we're going to do with this Aquarius code here that we tried all this stuff with is we're going to get rid of this, right? So we're not going to see that in the middle anymore. This is the main file, right? So it's not supposed to be rendering anything, right? It's like a utility file. So we're going to get rid of the debug, and now this file is just blank. It doesn't actually show anything, right? We're going to go into the actual files that are going to call those functions to render it. So let's find the Aquarius file. So here's Aquarius right here at the top. We're just going to open it, and we're going to take the contents and dump it into SVG. So zoom out, render it, file, export to SVG, and then Aquarius1.svg, save that. Close this one, open up Aquarius 2, right, which is just the locator holes that are going to go on the tabletop, right? So file, export as SVG, Aquarius02.svg, save that. Okay, so we've gotten the Aquarius symbol done. Oh, also we want to go into here and we want to find that Aquarius symbol, and we want to snip it for our little archive of symbols we're working on. We want to, these don't have to be professionally cropped because it's just for our, we just want to know what's inside of this project, and so having little reminders is going to help us when we want to come back to this project years later. So this is Aquarius, so Aquarius.png. Okay, so that's Aquarius. Like I said, we don't have to crop it well. We just want like a little, we just want accountability to know like what's here in this project, right? So Aquarius symbol, this is a goat, so it's not, it's what is this, Virgo? Hold on, no, Aries. Virgo is the M thingy. Okay, I still haven't gotten these remembered. So this is a crab. That's a 69. Cancer. Okay, this thing that looks like no is Capricorn. Gemini. Leo. This is a scale, which is Libra. This is an arrow. Bow and arrow. Sagittarius. This is Scorpio. This is our cow, right? It has little horns. The cow is the Taurus. So Taurus and Aries, I'm getting confused. So the ME thing is the Virgo. So we have Virgo and Scorpio that look kind of similar. Okay, cool. So now that we have those all in place, we're going to do a git bash here. And we're going to, oh yes, oh thanks. Yeah, I'm just trying to figure out like a design for a table. And I'm trying to figure out, well, what kind of design can I put on a table and just get something that somebody's going to buy, right? And that's kind of what I'm doing. Anyways, let's do a git status and kind of commit this stuff, right? So git add dot, and I don't know what's up with my like repo here. I think it has too many very small files in it because this is, every time I've been doing this for quite a while now, it's been just lagging on me. So I might want to just create like a I might want to cut all my files and get rid of the version control history and just make another repo, because this is taking way too long. And I'm guessing it's all the little tiny files that have changes on them. So git status. Okay. Git commit -am, and this is Aquarius done. Okay, so the Aquarius symbol is done. And we're going to try to move on. We have one more symbol. We have one more symbol before we have, like, all the ZODIAC symbols, right? And so we're trying to do all of this art in with math. We're trying to do it all with math because it's just going to be easier for my product pipeline if all of these source files are in code. So I could draw these out, right? I could draw these out. I could, like, draw them painstakingly out in Inkscape, but then it just makes it harder to precisionally manipulate the symbols if the symbols aren't defined in code. So it's very difficult and slow to draw these with code. But the idea is that I have a lot more control when I want to start positioning these, scaling these, and doing all other sorts of transformations. So we're going to just roll with it this way. So now that I have that, I'm going to stop and I'm going to restart the stream because I want this video to be just for the Aquarius symbol. And we're going to move on to the Pisces symbols. So yeah, so I'm going to restart the stream. I'll be back in like a few seconds.